Okay, in this video, we will talk about the shear stress of a beam due to the transverse loading. We have learned different scenarios, like an actual load applied on the beam, a pure bending moment applied on the beam, and now we're talking about if we apply a vertical force. Essentially, this is the shear force because it's acting parallel to the cross-section areas. And this is so-called transverse shear, or the shear stress generated on a beam. We want to understand the shear stress distributions across the cross-sections. You simply want to know what the shear stress distributions along that beam. If we have time, we can talk about torsions. Okay, in this video, we'll talk about transverse shear. In engineering materials, we normally see this type of failure called shear failure, particularly in these cross-laminate timber structures or multi-layered structures. It happens because essentially there's some shear stress generated at the interface and cause the failure of the materials. And in more general case, okay, we need to consider what happens for this type of beams. Let's look at the example more simply. Okay, consider a cantilever beam composed of separate planks clamped at one end, and if all of these beams are bonded, okay, you apply a pure moment, right? If you apply pure moment, doesn't matter whether it's bonded or not, they will deform simultaneously, okay? Essentially, this is the pure bending scenarios. What if you apply a concentrated force perpendicular to the beam, like this? If the beam actually are not bonded in these several layers, they will tend to generate some shear or slides, okay? So in the interface, you do have some slides between each layers, and this is due to the shear stress. In some very slender beam, for example, if you're talking about a very slender beam with aspect ratio huge, and this shear stress generated by the vertical force is not very significant. However, if you think about you have a much larger, much thicker beam with this type of structures, when you load it, then the shear stress cannot be ignored. Okay, so shear stress must be considered in this case. And we know shear stress normally, whenever it appears, it's going to have this complementary shear stress. Whenever you have this shear stress generated due to your vertical force, you must have this complementary force. Okay, I think the top one should have a direction like that. So this is complementary shear stress. You always have the horizontal shear stress associated with this vertical one. Okay, so let's come to the pictures. If we have a vertical force, then it's highly likely we generate the shear stress across the section has an ununiform distributions. And how are we going to quantify that? Right. We've mentioned that already. The board, if it is bounded or if it's not bounded, there are different effects. Particularly if they are not bounded, we'll see this sliding effect due to the shear stress. Okay, and if we think about the cross sections, there's some type of warping effect. It happens if you see that kind of effect that only is kind of significant in some very thick So this distance, the height, is very huge. Then you can see that most likely is negligible, okay, in the slender beams. Right. Also, warping violates the Saint Venant's assumptions of plane section remains plane. So under that assumptions, if you apply a force far away from your boundary condition, we assume this plane still remain as a plane, not like this warping plane. Okay, right. So let's derive the shear formula here. The shear formula actually can be derived indirectly since it's not so intuitive as the actual deformation of flexural or bending variations within the cross sections. And to derive the shear stress equations, we have to use something like horizontal force equilibrium, and by using the flexural formula and also the relationship we have introduced, like the shear force is equal to the derivative of the moment against the distance x, okay, across the beam. For simplicity, the longitudinal shear stress will be studied and calculated first, which we mean here, this one. And because once we calculate the longitudinal one, right, then what we can do is we can use the force equilibrium, and shear force has the complementary shear stress. So essentially, we can work out the actual transverse shear stress as well. They are equal. Okay, for any type of beam, if you look at some area, okay, inside that beam, okay, when you analyze it, you will see, okay, just take a small area and do the analysis. For example, this case, this is like a shear stress in a complementary manner, okay? So let's just derive it. In this case, we need to think about, okay, for arbitrary loading conditions, we take a small piece of area, okay, for example like this, and we took the gray area, just the top area, that small part, for the one we want to analyze. Okay, this shaded area has a distance y prime, okay, this distance to the neutral plane y prime, and it still need to follow this force equilibrium, and that means all the force, for example, in the x direction, x is this directions, or x in this three-dimensional graph is these directions, has to be equal to 0, all the force adding up, okay? This has to be equal to 0. And when we look at that small element, what kind of stress or what kind of load it is subjected to. So first of all, since we need to consider a moment load, when we consider force, we need to consider different type of loading, right? So for example, in this case, you have a moment applied on both sides, in the left hand side and the right hand side. And in this case, since it's not a pure bending moment, in that sense, there's other stress generated. For example, this shear stress has to consider to achieve the force equilibrium. In this case, okay, moment on the left and on the right, there's a slightly different increment, m plus dm, just to compensate the shear stress generated during the loading. Right, so this is the three-dimensional figure. It's a bit complicated, okay? We just need to look at the 2D version in this case. Now we look at from the side. Okay, on the left hand side there's some ununiform stress generated, okay, on that surface. On the right hand side, let's assume some stress that is not exact same, okay, because we have a shear stress here, we need to consider it shouldn't be the same, because if we consider the force generated from the horizontal plane, there has to be these three contributions has to be adding up equal to 0. Right. So let's look at this image and write the force equilibrium equations. There's three different contribution. Number one, let's look at the moment generated here, which is FA. In that small area, okay, we just need to look at that small area. If you look at 3D, should be the area here, A prime, okay. At that, let me just highlight that small area, A prime, and the stress generated on that face is sigma, and we do the integration across that area dA. Now that, okay, let's think about the sign of that moment, because the sign of moment is going clockwise. Clockwise, as we have defined, is negative, so there's a negative sign here. And on the right hand side, there's another moment generated, so we need to consider again left and the right have the same amount of area, so again A prime, and the stress now is different, sigma prime dA, okay. And also you have the shear stress times this cross-section area. You need to consider the through the thickness depths, basically the depths across the plane, okay. So that's T. Due to the shear stress, we convert shear stress to the force, right? We calculate force here. So now X is again in this direction, so this should generate another force imbalance, okay. So in this case, let's write tau times the cross-section area T dx. Dx is this distance dx must equal to 0. Okay, we don't know the sign here yet. We just assume tau is in that direction, so should just add a plus here. Okay. Now the question is how to work out this equation, because we have a sigma here. We know the relationship of the bending stress. Sigma here is the bending stress, right? Is equal to the moment over the y times the distance. Is depending on the distance at the edge. So the y the maximum, then the sigma is also the maximum. So we times y. So we substitute that relationship to these equations. Now we can plug in, that is m over I and y dA, right? And plus A prime, then sigma prime, because now the moment has changed. The moment has the actual increment dm, okay? dm over I y, right? So again, you need to remember there's the distance here we defined, okay, is y. Let's just consider here, right? So let's write that m plus dm over I y dA, okay. and we still leave that part here, we don't touch it, equal to 0. And you find these two terms, if you expand the term here, you will find this part can be cancelled by the same term around here. So it will shrink to a formula like a prime, then we only left the incremental part dm over I y dA, okay, plus the tau t dx equal to 0. Right. So now we rearrange the equation. Tau is equal to, okay, in this case we have a minus sign here, I t, and dm dx. Okay, dm over dx essentially is because we rearrange the equation, dx divided by everything divided by dx, and we just keep this y, now is the variable is inside of the integration, right? And we know the relationship here, v equal to dm dx, as we mentioned. And also q, this is the first moment of inertia, we have learned that before, a prime y dA, okay? That's sometimes also equal to the centroid position of that small area times the small area a prime, okay? So essentially we can substitute this relationship here, so and simplify this, then equal to minus, okay, v is this part, okay, and q is the second part over it. So that's essentially how we derive the equations. The sign here doesn't matter too much. It highly depending on where you define the x-axis, okay? And now, if you see a clear pictures, which is this one, essentially telling you, okay, tau here is equal to vq over it. That's the final equation of the shear stress, okay? Let's just forget of the negative sign here, and because this highly depends on where you define x-axis, doesn't matter too much, right? And shear stress in this case, right, equal to this formula. And if you dig it a bit more, you will know, okay, shear stress at a point y prime from the neutral axis is denoted by these equations. V is the internal resultant shear force acting, okay, on that cross-section plane. I is the second moment of area, or you can call it moment of inertial, and T is the width of that beam cross-sections, which is here, shows here T, and Q is the cross-section first moment of area, right? So now we have these formulas, and you can substitute some values. For example, for a typical rectangular cross-section beam, we want to work out the value for the shear stress. You substitute the first moment of area equations. You can work it out, okay? So talking about any small areas on top, this gray part, and you know you need to use the average, the centroid position of that small area to the distance of to the neutral axis. So essentially y prime average should be equal to what? Equal to this y plus that small distance, okay? That small distance essentially from here to here, very tiny here, okay? That distance should be equal to, right, half h minus y, okay? So essentially this distance divided by 2 is this one, and this part times what? Times the area of that part. A minus A prime essentially is half h minus y times the thickness here, B, okay? So substitute that to this equation, you have Q, denoted by this equation, go to here. And you know the cross-sectional beam is a rectangular, and the moment of inertia is 1/12 bh cubed. And you can simplify to these equations, right? So it is essentially, you know, the shear stress distribution is a parabolic equations. Okay, it's determined by this part. And when y, okay, you can try some values here. When y equal to 0, this value reach the maximum. Y equal to 0 means the neutral axis place here happens here, reach the maximum value, and y equal to half h. Okay, so y equal to half h, and you substitute the value here is y squared is 4h squared. That means tau becomes 0 at the edge. Okay, so essentially that's the distribution here we kind of visualize here. And here in that cross-section plane, we're just using different size of area to quantify the intensity of shear stress. Essentially, at the edge is almost tiny 0, and in the center, you can see the area become larger. And to quantitative showing that equation essentially is this parabolic equation. Okay, so shear stress follow that distributions. Okay, essentially if you think about the shear stress also has a complementary horizontal distribution, so it should denote like that. It's also fine. Okay, right. So that gives us the answer of the shear stress distributions. In the neutral axis have the maximum, which you can simplify that with equal for this type of cross section is equal to 1.5 V over A. Okay, very simple. Right, for some other type of cross section, you do need to do more work, and you need to find out the I is changing, and also the thickness is changing from the flange to the center beam. Okay, so that's why we actually see something like a jump from 0 jump to here, because suddenly your cross section become narrow and then jump to that area, right? So if you have time, you can go through this example here to understand how to calculate the shear stress distributions in a different shape like this one. Okay, let's stop here, and we can have some time to discuss how to work it out in our interactive sessions. Thanks.